Entanglement is a unique form of correlation that exists only in quantum mechanics, and it has such profound implication that people such as Albert Einstein had really trouble believing that quantum mechanics was complete, because once you understand this property of entanglement, you find out that it leads to things that he called, for example, the spooky action at a distance, when the action in one place instantly influences what happens in another place. And it also leads to having systems that lose their individuality but only exist in relation with each other, like two people of the opposite gender not having a gender of their own, but only being defined as being the opposite until you go and check what their gender is. I'm not going to be able to really explain what entanglement is, but what I will try to do is to explain what it is not. It is not just a form of correlation. And to explain that, I have prepared for you a simple piece of paper where I have written in blue a +1 on the left and a -1 on the right. So these numbers are anti-correlated. They are the opposite of each other. And then on the back side of the paper, in red, I've also written anti-correlated numbers, a -1 and a +1. What I can do now is to break this piece of paper and fold it and pretend I haven't seen what numbers are on it. And for example, I could give the right-hand side of the paper to some other person who is catching a plane to a distant city and agree that tomorrow night at midnight, each one of us looks at what numbers are on our piece of paper. So tomorrow night at exactly midnight, I could take my piece of paper and read the blue side and find there is a +1 on here. I now instantly know that the other person that could be on another continent has a -1 written in blue on his piece of paper. Now, does this violate relativity? Does this cause some conceptual problem? Well, no, because the information is not in these numbers. The information is in the correlation. The reason why I know that there is a -1 on the other person's paper is because I know that the numbers are anti-correlated. But that knowledge was already with me. It wasn't transmitted faster than the speed of light from the other person to me. So that's all perfectly fine. But quantum entanglement goes beyond this. And the only way to explain that is to show that classical entanglement obeys something called a Bell's inequality. John Bell was a famous quantum theorist who came up with a simple proof to show how different from classical correlations the quantum entanglement is. What you need to do is simply this. Calculate this quantity that I call m, that is the product of all the pairs of numbers on that piece of paper, so on the left and on the right, in red and in blue. But the second one here has a minus sign in front. So you can rewrite this formula as the left red multiplies the right red minus right blue, plus left blue that multiplies right red plus right blue. And from this, it should be easy to see that there's only two possibilities. If the numbers on the right-hand side of the card, on the red and the blue side, are the same, then this is 0. But if they are the same, it means they're either both +1 or both -1, then this must be +2 or -2. And then this can be plus or -1, so in total you will get +2 or -2 out of this. And the same happens if the two numbers are opposite, then this will be 0, and this will be either +2 or -2. And so again, you get +2 or -2 from the whole formula. So no matter what choice you make for the type of correlation, and no matter how many times you repeat the generation of these numbers, you can certainly know that the average value of this quantity will be some number that's between -2 and +2. So this is called Bell's inequality. This is all very simple, but if you take quantum entangled particles, you will find that depending on how you observe them, you can get a number that is between 2.8 and -2.8. Now, I want you to take a really deep look at this simple formula and try and imagine how do you get a number larger than 2 from this if all you have is products of +1 and -1. You really have to think outside the box here. The only way to do it is if the numbers on the right-hand side of the card are not pre-written there. They don't pre-exist, but they are correlated to the number on the left-hand side of the card, and they depend on whether I'm reading the red or the blue side of the card. In other words, if I decide to take my card on the left-hand side and read the red side of the card, these numbers might be, for example, opposite. So this becomes a positive number. Whereas if I decide to read the blue side, then these numbers would become the same. And then this is also a positive number. And overall, I get a number larger than +2. So this is essentially how you get, 1, the non-locality of quantum mechanics. The numbers that appear on the right-hand side of the card depends on which side of my card I decide to read. That's the spooky action at a distance. 2, the correlation is already there, but the numbers are not pre-written. There is no number written on these cards until I decide to read my card, at which point a number appears and a correlated number will appear on the other side of the card, but which number appears depends on which side I've decided to read. This only exists in quantum mechanics and in one of the most profoundly important properties of quantum physics that is at the basis of a lot of quantum technologies such as quantum communication and quantum computation.